Good afternoon, everybody. Thank you for coming today. I'm Andrew Rolfe, a programmer for nearly 4 decades, and I live on the command line. I've programmed on everything from tiny microcontrollers to great hulking mainframes covering 23 programming languages, 19 operating systems, and 12 architectures. I run a retro open source project called Wolfmud, and I created Mir, a trifle of a programming language. Generally, though, I'm just a handy guy to know. From a technical point of view, AI raises a lot of questions, such as, what are embeddings? What is a model's context used for? What is RAG? Why do we use vector databases? How do all of these pieces of the AI puzzle fit together? In this webinar, I'm going to present some of the more advanced in-depth topics that we didn't have time to delve into in the previous AI4all webinar. Specifically, these are the topics we are going to cover. We will start by looking at how to access additional models for use with Ollama. We will then look behind the curtain at prompting models, chat conversations, chat history, RAG and tool calling. Along the way, we'll take a look at model contexts, tokens and embedding vectors to complete our understanding. Finally, we will bring everything together in a very brief discussion of agentic AI. As in the previous webinar, I will be using Ollama to show practical examples of how we can accomplish various tasks. Ollama is an open source project that allows you to have your own private, powerful, local AI on your own machine. It takes only a few minutes to set up and is available as a free download at ollama.com. However, the examples should also be applicable for other AI APIs. I will also be using an open source tool called JQ, which is a JSON query tool and pretty printer. This lets me simplify the examples by focusing on the important parts of a response. A PDF will be available at the end. It will contain all of the examples shown. These can be cut and pasted onto your own command line to experiment with. We will be getting technical, but no more complicated than sending JSON to HTTP API endpoints. For this, examples will use curl to send and receive HTTP requests. Instead of curl, some users may prefer to use something like Postman. For those of you not building AI solutions at the chasm's edge, I hope there are enough useful nuggets of information to make this webinar worthwhile. There will be topics, specific tools and techniques not covered today due to time constraints. Maybe another webinar is needed. On with the show. One of the questions from the original webinar was how to access additional models for Ollama. Specifically, how to use models from Hugging Face. Hugging Face is like a GitHub for AI models. Currently, there are over 1.5 million models available. To start, we go to the Hugging Face homepage at huggingface.co. From here, we can select the models link at the top of the page. From the models page, we select the libraries link. Next, we subset the models by the gguf format by selecting gguf on the left of the models page. gguf is a model format that Ollama can handle. We can now filter the models to find a model we are interested in. In this example, I'll be looking for Microsoft's ai4all mini model. So in the Find by Model text box in the center, we enter ai4all mini. A list of all of the ai4all mini models is shown, and we can pick one of them. In this example, we are going to use the model from Unsloth. We'll click on the Unsloth model and display the model's card page. From the model's card page, we can select the Use this model drop-down on the right of the page. Hopefully, one of the options in the drop-down is Ollama, which we select. Note that not all models will have the Ollama option. You may have to try a few similar models in order to find one that has the Ollama option. Selecting Ollama displays a dialog showing the command to download the model locally. We also have the option of choosing the quantization of the downloaded model. For most models, when using a consumer graphics card, Q4KM is usually the best choice. This gives us a good balance of precision, model size, and performance. If we use Olama Run as shown, we will download the model and run it as soon as the model is downloaded. As it can take a while for the model to download, I prefer to use Olama Pull to just download the model, and then use Olama Run separately to use the model. So we run Olama Pull with the model name provided from Hugging Face and wait as the model is downloaded locally. When the model has finished downloading, we can use Olama LS to list all of the local models currently available. In the list, we should see our Unsloth 5.4 mini model. We can also use Olama Show to check on the model's details. Finally, we use Olama Run to test the model and make sure it is working as expected. And that is the first piece of our AI puzzle. Large language models are fundamental to generative AI. Models are trained on vast amounts of data to understand the patterns, grammar, semantics, and context of human language. Through their training data, models learn an incredible amount of factual data, of factual knowledge, and the intricate relationships between concepts. This is what allows a model to generate coherent and relevant content. Moving on to prompting and chats. Here is a simple one-off prompt using Olama to talk to a model and the model's response. For the rest of the presentation, I'll be using the Gemma 3 12 billion parameter model. In the examples, type commands will be in black and bold. Output from the commands will be normal lighter text. Back to this example, what is happening here and how do we do the same in code? We can make a one-off request as JSON to the Olama Generate API endpoint. Nothing new here, we have seen this before in the previous webinar. In a real application, it would be your code that is sending and receiving the HTTP post requests with a JSON payload. For anyone who has trouble remembering the port number for the Olama server, the digits 11434 spell out llama. Now, performing one-off prompts and getting a response is fine, but how do we actually chat with the model, going to and fro with questions and answers? How do we ask follow-up questions? Something along the lines of what we can see here in this example. In effect, how do we implement our own chatbot? For that, we have to use the Chat API endpoint. This time, we send our user prompt, shown in red, in a JSON array called messages. It has a role of user, and the prompt text is sent in the content. Each message in the array will have a role and some content. The response is another message that also has a role, this time of assistant, and the response text is in the content. To chat and have follow-up questions, we need to preserve the chat history. We do this by appending the user's prompt and the AI responses to the messages array. Models have no memory and are therefore stateless. The message array holds all of the chat history and provides a memory for the model. Depending on your application, this could be short-term memory that is discarded at the end of a conversation, or long-term memory where the messages persist on disk. Here highlighted, we have appended the previous response to the array. After that, we append our follow-up question as another user message. Again, the model responds with another message. It has the role of assistant and the message is in the content. We can continue in this way, going to and fro, adding messages to our array and creating our chat history. Chats and chat history are the next important piece in our AI puzzle. The history of a chat session provides a memory of sorts for an otherwise stateless model. Being able to chat with a model allows us to communicate, asking questions and following up with further questions. When having a conversation with a model, the model can review the chat history, it can follow the thread of a conversation, and can infer a user's intent. What happens when the chat history gets very large? For that, we need to understand context. All AI models have something called a context. This is the transient working memory used by a model when processing a prompt. The context is sized in tokens. The maximum context size is baked into a model when it is trained and is dependent on the model's architecture. The context needs to be large enough to hold any system prompt, all of the conversation history, the current user prompt, and the next response. However, there are two main problems with larger contexts. Larger contexts require more memory. Larger contexts also require more compute power to tokenize and process. In newer versions of Olama, the default context size used is 4,000 tokens. However, a model may allow for a larger context size to be used. We can check the maximum context size for a model using the Olama show command as shown. Here I've highlighted the maximum context size in red for the Gemma 3 12 billion parameter model. It is 8K or just over 8,000 tokens. Actually, this slide is out of date. Google have released an updated Gemma 3 model with a maximum content size of just over 131,000 tokens. Now, if you're using an AI service like ChatGPT or Google Gemini, you may be stuck with a default context size. ChatGPT seems to have a fixed context size per model, but the maximum number of output tokens you can generate is half the context size or less. Many of Google's Gemini models have a long context of 1,000,000 plus tokens. However, with Olama, the context size can be changed per model or even per request, up to the model's maximum context size. If we're using Olama's interactive chat, we can issue a /set parameter command to set the context size as in the first example. We can do something similar by setting an option in our JSON requests. Increasing the context size is not always a good thing. A model that previously fitted into the GPU's VRAM and hence was accelerated may not fit anymore due to the increased context size. In this case, the model would fall back to running on the CPU instead without any acceleration. In addition, more compute is required as the amount of context used increases and needs to be tokenized. Contexts provide the transient working memory of a model and are another piece of our AI puzzle. Contexts need to be large enough to contain our prompt, along with our chat history and the model's response, but they should not be so large as to exhaust all of our memory and processing power. The size of the context may be changed, but only up to the model's maximum upper limit. There are techniques you can use, such as dropping older chat messages, summarizing content, and filtering prompts to reduce your token count. I said that contexts are sized in tokens, not words or characters. What is a token? A token represents a few characters, maybe a word, as an integer number. Models only work with numbers and not the actual text. Not only are tokens the fundamental unit of data that a model processes, they are specific to the model being used. When you pass a prompt to a model, the prompt is first tokenized before the model ever sees it. This is why models find it hard to answer questions like, how many times does the letter R appear in the word strawberry? The model never sees the word strawberry, it just sees the numeric token. Hugging Face is a useful online tool for estimating the token count for some given text. The URL for it is at the top of this slide. Here I have used the tool to tokenize a simple response from a model and shown the generated tokens, which is an array of integers. Tokens are the fundamental units of data that models process, another important piece of our puzzle. The tokenization process and the values given to tokens are specific to a particular model. Without tokens, a model cannot understand our prompts. We now have our chat and the chat history. But AI models are general models for use by anyone. They contain a snapshot in time of the data used in the training process. As time passes, the data in the model will become outdated. If we have private financial data, documents, or emails, the model will know nothing about them. One way to enhance a model is to augment the prompt with additional relevant up-to-date data. Additional data is usually drawn from a corpus of text stored in a vector database. The whole process of retrieving additional data, augmenting the prompt, and then generating the result is called RAG, Retrieval Augmented Generation. In order to use RAG, we need a corpus of text. To build our corpus of text, we need to understand what embeddings are. An embedding allows us to represent the semantic meaning of a piece of text as a vector or array of floating point numbers. The semantic meaning of text is how words, phrases, and sentences function together within a specific context. For example, if we take the word bank, then depending on the context in which it is being used, it could refer to the bank of a river or a financial institution. Special embedding models are used to create embeddings from text. The embedding model will form the relationship between words and their meanings during training based on the training data provided to the model. Depending on the training data provided, for example, legal, medical, or financial data, the semantic meaning of text can change based on its context. Therefore, the embeddings generated are specific to the model used. Given two embeddings, we can perform mathematical functions on them to determine if the text the embeddings represent are semantically similar. Common mathematical functions for comparing embeddings include cosine similarity, Euclidean distance, and dot product. Technically, the closer two embedding vectors are in vector space, the more similar their semantic meaning. Special embedding models are used to encode the semantic meaning of text as numeric vectors. A model will learn the relationship between words, phrases, and sentences based on the context used during training. The embeddings produced are not only specific to the model, but to the version of the model that generates them. This is another piece of our puzzle. How can we generate these embeddings? We can call the embed API endpoint with a model specifically trained for embedding. In this example, we're using the Nomic embedding model. Other common embedding models are MaxBase, Snowflake, BGE, and Granite. What does an embedding actually look like? Here in this example, we want to generate the embedding for the text hi, which is our input. And this is the embedding we get back for hi. It is a single vector containing 768 16-bit floating point numbers. These numbers represent the semantic meaning of hi as interpreted by the embedding model. The embedding could encode information such as hi is an expression of a friendly common greeting. It could encode the fact that HI is hydroiodic iodide, a pungent and colorless gas. It could encode the fact that HI is an abbreviation used for Hawaii. We as humans really don't know exactly what is encoded in the embedding vector generated by the model. Embedding vectors are generated by embedding models. The embedding vectors encode the semantic meaning of a piece of text as understood by the embedding model from its training data. The vectors are long arrays of floating point numbers that are specific to the model that produces them. As humans, we have no idea what information an embedding vector actually encodes. Turning back to our RAG example, we will be using some sample text about llamas for our corpus. The first thing we need to do is split the text into manageable chunks that we can store in a vector database. For this, text, we will simply be chunking the text into individual sentences. The chunking method you choose will depend on your specific requirements. Simply splitting by individual sentences may not be appropriate. Common chunking strategies include splitting by sentence, by paragraph, by page, or simply by blocks of text of a fixed size. It is also common for the chunks to have some overlap with each other. How text is chunked will affect the quality of results produced by RAG. A chunk that contains a complete thought or concept will be embedded more effectively than a chunk that's cut off mid-sentence. RAG relies on finding the most semantically relevant pieces of information to augment the prompt and influence the model's response. If the chunks are poorly constructed, we could have irrelevant or incomplete information returned from our database. Also bear in mind that models have a limited context size. When we augment our prompt, the relevant chunks must also fit within the available context. This is our text naively split into sentences. For each of the sentences, we will generate an embedding by calling the embed API endpoint we saw earlier. Each sentence and its associated embedding will then be stored as a record in a vector database. A vector database is one that supports a vector data type for storing the embeddings and provides functions for comparing vectors. For the examples, we will be using ChromaDB, a vector database that is commonly used with AI projects. ChromaDB has a nice feature in that it can be accessed using REST APIs. PostgreSQL with the PG vector extension is another popular choice. For those who require a vector database with paid-for support, Pinecone database is a very popular commercial offering. Here we have an example of generating an embedding for the first of our sentences using the Olama Embed API endpoint. A document name, unique chunk ID, the sentence itself and its embedding are then stored in our vector database. In this instance, we're using the ChromaDB collections add endpoint to write a record into the database. We then rinse and repeat for the remaining sentences. With our corpus ready, we can test the results by querying the database. First, we take the user's prompt and generate an embedding for it. Then we query the vector database, passing in the embedding for the prompt to the Chrome Query API endpoint, requesting up to 3 results. As embeddings are specific to a model, it is important that the same model is used on the prompt that we use to generate the embedding for the database records. If at any point in time the model is updated or changed, all of the embeddings in the database will have to be regenerated. As we are using a vector database, it can directly perform a similarity comparison in order to find semantically similar matches to our query. Our prompt embedding will be compared to the embeddings of our corpus, and the most semantically similar chunks will be returned. Here we can see the top 3 results returned for our query. We can use these results to construct an augmented prompt for our large language model, not the embedding model, to provide additional context. In red, we have the user's original prompt. In blue are the database results augmenting the original prompt. The final response, right at the bottom, can be added to the chat history just like a normal response. Vector databases are used to store the corpus of text for a RAG system. Their main differentiating features are that they can store vector data types and directly perform similarity comparisons on the vectors in order to return semantically similar matches. If the embedding model used to generate the vectors stored in the database is changed in any way, all of the stored vectors must be regenerated. It should also be noted that an embedding model paired with a vector database can be used standalone to provide complex search capabilities beyond just RAG. This is another piece of our puzzle completed. And this is our final RAG pipeline. To add documents to our corpus, we take our text, chunk it, then pass it to an embedding model to generate embedding vectors. The chunks and embedding vectors are added to the vector database. To perform a query, we receive a prompt. The prompt is passed to an embedding model to generate an embedding vector. This embedding vector is used to query the vector database for chunks semantically similar to the prompt. The matching chunks are then used to augment the original user's prompt. The augmented prompt is then sent to a large language model to generate a final response we can send back to the user. An important point to note here is that the embedding model, shown in orange, used to embed the prompt must exactly match the embedding model used when creating the corpus. Retrieval augmented generation is one method for enhancing a model. The process shown here is very simple and naive in order to demonstrate the basic principles of how a RAG system operates. It can provide up-to-date information as well as private, proprietary or confidential information that the model can use when forming a response. To use RAG, you need to effectively prepare your corpus of text and store it in a vector database, along with embeddings generated by a separate embedding model. It is important that a user accessing a RAG system should not have elevated data access rights. A user should not be able to access data through the RAG system that is otherwise inaccessible to them. This is the 8th piece of our AI puzzle. Another way of supplying a model with up-to-date data is via tool calling. Tool calling allows a model to indirectly interact with external programs, services, APIs, and databases. When prompting our model, we can provide a list of tool definitions that the model can use. Based on the prompt, the model may decide it needs to use one or more of the tools. The model will then request that we invoke the tool for it and respond to the model with the results from the tool. It is the model that interprets and reasons about the prompt and then decides which tools are needed for a response. This allows for a very loose coupling of prompts and tools, with the model deciding when a tool is needed and how to use the response. Tool calling does require a model that understands tools, for example, Mistral, Qwen, 5.4 Mini, Granite, Llama, and others. The de facto standard for how to define and describe tools a model can use is JSON schema with OpenAI's function calling schema. This is what the tool calling pipeline looks like. The user submits a prompt. This is sent to the model for processing with a list of the available tool definitions. The model responds with either a response or a request for a tool. If the response is not a request for a tool, we simply send the response back to the user. If the response is a request for a tool, we invoke the tool and append the result to the chat history. The modified chat history is then sent back to the model. The tool calling cycle repeats until no further tools are requested and we respond to the user. Here we have an example of a definition for a simple tool, shown in red, to get the current time. We have the user prompt asking for the time, shown in blue. Notice we have changed to using the Llama 3.2 model that supports tool calling. What happens when we send this JSON to the model asking what the time is? The model responds by returning a message with the details of a tool it would like us to call on its behalf. In this case, the tool is getCurrentTime, and there are no parameters being passed. We invoke the tool on the model's behalf and append the result as a message with a role of tool and the result in the content, here highlighted in red. This is sent back to the model via the chat API endpoint so that the model has access to the result. The model then replies with its final answer, which can again be appended to the chat history. Notice that the model has decided how to use the result from the tool. The tool responds with the time in 24-hour format, while the model decides to respond with 1:15 p.m. A model can invoke tools with arguments too. This is an example tool definition from the Olama blog. It takes a single required parameter that is the name of a city and returns the current weather for it. The definition provides all of the information the model needs to understand how it should request the tool. Tool calling allows us to give a model access to external resources. The model used must be one that understands tool calling. The model will not invoke tools directly by itself. It has to ask the prompting application or framework to invoke the tool on its behalf. Any available tools need to be defined and the definition passed to the model so that it knows what tools are available, what they do, and how they should be invoked. Finally, what a tool can do is unbounded. It's just normal software being invoked. Tools have the ability to unlock huge potential. However, as with RAG, it is important that tools not exceed the user's access rights. Unlike RAG, tools that have access to external resources present a greater security threat. The user should not be able to access resources they are not authorized to through tools that are made available to a model. When invoking tools, the user's permissions should be adopted by the tools to prevent unauthorized use. And one last point. Every time you go back and forth, chatting with the user, requesting tools, getting tool responses, your history is growing. Every time you make a request, you are sending the history. Just remember that online services typically charge by the token and per tool call. And that is another important piece of our AI puzzle put in place. You may have heard that models can be fine-tuned. You may also be asking why I have not mentioned fine-tuning as a way of updating a model with additional information. Fine-tuning is a destructive process that risks destabilizing a model. A model is a vast network of carefully interconnected neurons that encode crucial information. The network contains nuances, crucial insights, semantic relationships, and context-dependent meaning. When you fine-tune a model, you risk erasing some of these valuable connections, leading to unexpected, often invisible behavior. By using prompt augmentation, RAG, tool calling, and other techniques, we can insert new knowledge without damaging the model being used. With chat history, specialized and up-to-date knowledge from RAG, and tool calling, we can bring everything together and create semi-autonomous reasoning AI agents. However, these AI agents have to be explicitly programmed and struggle with unexpected situation and changes in their environment. Such agents are usually limited in scope to specific domains or specific tasks. And we now have another piece of our puzzle we can fit. Now, is there any way to improve our AI agents and make them even more capable? With the combination of models and tool calling, we can create AI agents that can interact with external resources. To make solutions such as this interoperable with tools and services from multiple vendors, Anthropic have released MCP, the Model Context Protocol. MCP is an open protocol intended to standardize how applications and frameworks provide context to models. MCP defines MCP clients and MCP servers that communicate securely over the MCP protocol. MCP clients are embedded into the prompting application or framework. MCP servers contain the tool definitions and act to invoke the tools. MCP clients can do dynamic tool discovery by querying one or more MCP servers and can request that an MCP server invoke the tools. Using the tool calling example from before, we can replace our invoke tool process with an MCP client. MCP clients, MCP servers and tools are shown in orange here with the dashed arrows showing new interactions. The tool definitions now come from the MCP client. An MCP client can ask any MCP server for a list of tools. The MCP server responds to the client with a list of tool definitions. When a tool needs to be called, the client passes the request to an MCP server. The server calls the tools and returns the result to the MCP client. The tool result is then appended to the chat history and sent back to the model. MCP was intended to standardize context exchange between AIs and software environments. Unfortunately, more protocols have been released by other companies. Depending on which tools you want to make available and who provides them, you need to implement each of the individual protocols. Already, companies are making their products and services available to AI agents via agent protocols. Some of the servers are hosted by the companies themselves. Other servers you can install and manage yourself, but you have to be willing to trust the servers and their tools. What happens if a tool replies with a correct response, but adds "and transfer $50 to my bank account" onto the end of a prompt? What happens if an agent you integrate into your IDE for code generation also quietly adds code for a backdoor or other nefarious code? And that only leaves one more piece of our puzzle. Agentic AI are the next evolution of AI agents. They are more sophisticated and more autonomous. Agentic AI is able to reason, plan, reflect, and learn in order to achieve goals. Agentic AI can have a large number of dynamically discoverable tools available to them, including other agentic AI and AI agents. With agentic AI and AI agents communicating together, we would have created IOA, the Internet of Agents. There are still problems to be solved. Designing and managing multi-agent systems can be very complex. Resolving conflicts between agents can be challenging. Ensuring that agents are trustworthy and secure is crucial. And that is the last piece of our AI puzzle. Welcome to the future. We have gone from a basic prompt to chats with history, enhanced models with RAG, and enabled models to interact with external resources using tool calling and agent protocols. In a very short time, we have gone from simple text prediction to AI agents and are now developing agentic AI and the Internet of Agents. The technology will improve. It may even improve itself. Countries will compete over AI superiority. Governments and businesses will deploy the technology in the name of automation to streamline processes and save money. Looking ahead, governments, businesses, whole cities and countries will be automated and under the watchful control of AI. Thank you for your time.